All right. Awesome. Okay. So as I said before, welcome to this Physics 1A class at UCLA. My name is Martin Toderi. I'm going to be your teacher for this course. Remember, this is kind of an intensive course, so please try to follow the topics and the lectures. So we have class every day, remember that, and you have a discussion session with RTA Kate Holwick, and there you're gonna follow the topics of the week, and you're gonna practice. So let me just move forward to the first slide. Second slide says, as I said before, so my office hours for this week are gonna be this Tuesday at 2:30 p.m. That might change, so that's why I'm just telling you now for this week, because I need to tweak something I have on this particular week. But Kate has already told you guys and that her office hours will be from 9 to 11 on Fridays. And of course, you have the discussions with her. So any concerns about that, you can contact her. And regarding contacting me, please, if you need to contact me by email, please do it, for logistic reasons. Try not to send me questions of problems and stuff like that. So just we can get together on the office hours and look to look any concern you have or any issue with the problems. So we have our class website. I think everyone is in there. I enabled the Pearson's website yesterday, so you should be able to enroll. If you're not enrolled yet, please do it so you can complete the homework assignments. So these homework assignments are pretty much multiple choices, so you can complete them and get the response and get the actual get a complete right after you get it done. And then we're gonna have problem sets. So you're gonna go over them. Some of the problems in my class, some of the problems will be resolved during discussion sessions, and those proposed problems for discussion sessions, you're gonna upload them after through Gradescope. I guess everyone is familiar with Gradescope. If not, of course, you can always ask. But from that you can get some credit. So just to give you a heads up, we're gonna have a midterm on August 28th. This will be during class. Unfortunately, some people ask about having a different time for the exams, and that's not possible. So we need to have the exam during respecting LA time, so we cannot shift the actual time of the exam. So it will be during class on August 28th, and the final exam is fixed for September 15th from 10 to 1 p.m. Unfortunately, we cannot change that, right? This midterm will be basically, half of the course from chapters 1 to 7. And the final will be a review of the whole thing from 1 to the final chapter. If we can get, I guess we will get to the last chapter. In terms of grading, the final would be 50% of your grade, midterm 30. So both exams are gonna be a big part of your grade. Discussion sessions, as I said before, is just showing that you are participating in the class and you are understanding topics. So we'll be just submitting the proposed problems. You won't be graded those problems won't be graded. It's just the fact that you're working. Homework, that will be 10%. As I said before, those are the multiple choices from Pearson's. Those are fairly easy, I would say, and you'll have a whole week to complete them. And then if you want to do extra credits, to get from an A to an A plus or a B to a B plus and so on, you can do an extra section so you can get extra credits. Okay, the tentative schedule for the course is, I think you've seen this in the syllabus, but in case you haven't seen it, I mean, the course is 6 weeks, so we are covering, the basics of physics, so bear that in mind. So we cannot stay back, we cannot take the take a lot of time in each of the topics. So please keep up with the topics. This first week, we're gonna see vectors, units, one-dimensional motion in 2 and 3 dimensions. And then I will introduce the topics for each week. Okay, so I guess we can directly jump in. Just let me check one more thing with the people here. Okay. Cool. All right, so let's just jump into today's topic, which is units, physical quantities, and vectors. So let me go here, enable this. You see the pointer, right? Yeah. Okay. So why physics, right? Why do we care about physics? Why do we, why do we study physics? Basically because we want to predict things, right? Physics is letting us predict what happens around us, what happens in the world, what happens with things, with choices that we make, with things that we create, etc. So this is why physics it's important, right? To engineering, to biology, to astro, to whatever science you're studying, whatever thing you're trying to figure in the world is going to have something to do with physics, basically because you need to know, you need to have information, and information is what lets you take good decisions, right? So basically we want to predict things. So physics is an experimental science. So we try to see patterns in nature, right? And when we find those patterns, we try to explain them. And that's the way we start building up physical theories, like the Big Bang, quantum field, theory of relativity, things that humanity, science in general, has come up with to explain nature phenomena. So once this theory is very well established, we call it a physical law or a principle. So that's how we arrive to Newton's laws of motion, gravitation. We get Archimedes' buoyancy principle, thermodynamics, all the fundamental stuff that's basically constituting physics. And of course, these things have to be proven in time, and they've been, right? Okay, so idealized models. So normally when we want to study some phenomenon, we have a bunch of characteristics, a bunch of things that are around that phenomenon. So let's see this baseball, for example, the baseball that's being thrown, which is flying over the air. So the baseball has a shape, right? It has a spherical shape, which is pretty complex, right? To describe, mathematically, or even, to think about how it's interacting, how the surface is interacting with a fluid, which is air. right? So we have air resistance, we have the rotation of a ball, we have the gravitational force, which is pulling it to the earth, basically. So in order to study this phenomenon, it's pretty, it would be much easier if we simplify this, right? So our model is a simplified version of the physical system that it will be too complicated to try to analyze, right? In full detail, to try to write all the math that's around that phenomenon. So for that, we just say that the ball, the baseball, is now a point. It's now a particle. So we've lost the air, and we say there is no air resistance, there is no rotation, right? But we keep the mass, because if not, we'll be ignoring everything. So just bear in mind, just have that idea that, you know, even though we would love to explain everything or about a natural phenomenon, sometimes we can, or sometimes it's too complex, or sometimes it's just wasting energy on something that it's not gonna really change our result, right? So keep in mind that that it's the most common thing to do. I don't know if you've ever heard of the spherical chicken, but or cow. That's the way a physicist will model a cow or an animal with, you know, 4 legs. Just ditch the legs. It's just a sphere, and that's it. Okay, let's continue to standards and units. So of course, we need some reference to describe the physical world, right? We need units. We need some standard, because if not, everyone will have their own language to describe nature. So that's why we have units, right? And a standard to do it. So any number that is used to describe a physical phenomenon quantitatively is called a physical quantity. So these physical quantities are related, are described, and are labeled with units, right? So we have, for example, length, time, and mass, which are the 3 fundamental quantities of physics, right? Because we need to describe, you know, we live in a 3D space. We are we are aware of the time that's passing, and of course we occupy a volume, and we have matter. So that's the mass that we need to describe the at least the basics of our, you know, our physical world. So when we measure a quantity, we need to compare it to some reference in order to say, oh, we have this number of this units, so we can all know, and we can all make sure that we are understanding each other, and we can do calculations, we can, you know, convey our results, etc. So the international system, that's SI for Système International, that's in French. So it's the most widely used system of units. So here in physics and in, you know, just science in general, you won't ever hear about inches or feet or anything like that. It's all meters, seconds, and kilograms. There are no pounds nor inches. So let's just take a quick look to those 3 quantities that I just mentioned. Let's start with the meter, which, I mean, it's pretty interesting to go over of how these quantities are defined today. So the meter now, it's defined as the distance that light travels in vacuum in an interval of 1/299,792,458 parts of a second, right? And that's not that's not a arbitrary number. That's actually the speed of light, which normally we can say that it's 300 kilometers per hour, 300,000 kilometers per hour. So per second, sorry. So so its symbol is M. So M is not an abbreviation, and you cannot use a capital letter. You cannot use a period or plural, right? So that's how it's defined today. But before, they just used this metal stick, which was, stored in a cabinet over a couple of hundred, well, yeah, 100 years. And so people just compare the meter to these pattern meter that was stored, and it was also defined as a 10 millionth part of half of a terrestrial meridian, right? But it's always, I mean, in the modern world, they've tried to define all these quantities, relating them to physical phenomena, to physical constants, basically, like the speed of light. Okay, so let's take a look at the time. So the time is measured in seconds, and you can see there that's Kronos, the Greek god of time. And until 1967, it was defined as a fraction of the duration of the mean solar day between 1750 and 1890. So you can see why it's 1 part over 86,400, because those are the seconds that are on a day, right? So if you do 24 hours by 60 minutes by 60 seconds, you get that number. But now the second is defined as, the duration of basically 9,000 millions of oscillations of the radiation of the transition between two hyperfine levels of the ground state of cesium atom. So that's the way, it can look kind of arbitrary, but it's cool to define it, to tie these things to natural phenomena that are not changing. That that emission of the cesium atom is not changing even if the sun explodes. There's no way that the second could change in the universe. So there is a picture of this atomic clock down here, which is in Switzerland, and it's crazy the precision that it has. Look, it has an uncertainty of 1 second in 30 million years. So the clock will not miss a second in 30 million years, and that's pretty much crazy if you think about that. Let's move to the kilogram. So our unit of mass, and the kilogram would be the most, I would say, traditional definition in this case, because it's been used until 2019. The pattern that it's stored in Paris. So the old definition comes from 1889, and until 2019 it was used. The problem is that the copied kilograms, from the pattern, they started changing, and they diverged by 50 micrograms. It's in 100 years, right? But there's still some changing. So they redefine it in terms of the constant, the Planck's constant, which is h. For those who are not familiar with it, you can take a look at that link that's down there. I just didn't include the whole thing because it's kind of beyond the course. So if you haven't heard about the Planck constant yet, it's a very, very important constant in physics that's gonna pop up sometime probably in your studies. Okay. Of course, we need more, more definitions than just mass, length, and time. So we have for everything, every quantity that we want to measure, we have a specific unit, right? And so, of course, some are very, very common. You probably heard about hertz, pascals, joules, watts. Watts is pretty common, right? Because it's a power unit. You always hear about watts. But of course, there are others that are not that common, like candela, which is luminous intensity, maybe mole if you haven't took a chemistry class. But yeah, I mean, there are a bunch of units around there because there's a lot of characteristics in the natural world that we want to measure. Okay, so we have, of course, we have multipliers of this of these units. So just bear in mind that these multipliers go by pairs of 10, right? So it's kind of straightforward, right? You have meter, you have decimeter, so you have a hundred, you have decameter, hecto, kilo, right? Centi if you want if you divide it by 100, etc. So that's pretty straightforward. But this lets us, take a look at the orders of magnitudes of those quantities, right? That's an order of magnitude. When we jump with a power of 10, we jump to another order of magnitude. So just to bear in mind that we are in the meter order of magnitude. So if the Earth is on the 10 to the 7th meter order of magnitude, distance to the sun 10 to 11, and so on. So we can characterize the order of magnitude of things with this multipliers, multiples actually. So a very important thing in physics is to be consistent with units, and that's gonna help you a lot when solving equations. And that's a fundamental thing that I always try to get the students to get used to. So sometimes you're not sure of what your result is, right? Sometimes you're not sure if you messed up at some point or something. But if you're changing the units, if you're getting, kilograms when you want to get length, then you did something wrong. So dimensional analysis, it's very, very useful to know if the result that we got is a correct result. So of course you can always change the units, right? Look at that example. So we have 30.2 centimeter square, and we can calculate how many meters squares are, because of course those units are equivalent in terms of the quantity that we are measuring, right? It's just a difference of magnitude. So in order to do that, it's useful to consider adding, multiplying by 1. So basically what you're doing here, right, you're multiplying by 1 in terms of 1 meter is equivalent to 100 centimeters, right? So we need to get rid of this. Let's say we want to go through from centimeters square to meter square. We need to get rid of that centimeter square and just keep this one here. So if we multiply by 1, let's say 1, this thing will still be conserving the magnitude that we want to convert, right? So units can be treated as basically can be operated as numbers. So the centimeter squares to the third centimeter yeah, to the third are disappearing, and we have a meter the meter to the third, right? And then we keep this thing here and we multiply it, and we have this meter here. So that's a fast way to do it. Of course, we can always just calculate how much a meter would be in centimeters, and just do a linear relationship. But it's an easy way to convert units. Okay, so let's just move on to the first topic, that would be vectors and scalars. So vectors are a very important quantity in physics. Why? Because everything that we're trying to characterize in our world is gonna have a direction, right? A direction in space, because we are in 3D space. So let's just take a look at the definitions here. So a scalar quantity can be described by a single number. So time, temperature, mass, density, for example, things, right? Those things have no direction, have no orientation in space. So time is just seconds, temperature, kelvins, Celsius, mass, kilograms, right? And a vector quantity has both magnitude and direction in space. For example, displacements, velocity, force. So everything that it's basically pointing somewhere in space. So we represent a vector by an arrow over the letter. Sometimes you will see the letter in block without the arrow, and that would still mean that it's a vector, but here we will use the arrow on top. And then we have the magnitude, or sometimes you can find it as module of the vector, which is a scalar quantity, which is just a number, and that this thing is always positive. So this thing is represented by the letter, the arrow, and 2 bars between them, or just ditching the arrow. And you'll be talking about the module, the magnitude of the vector. So if we represent this, let me continue saying this. If we represent a vector, we're gonna draw a line with an arrowhead at its tip. So that arrow will show where the vector is pointing. That's the direction. So let's see, we have let's say we have these 2 vectors, and they are the same, they have the same magnitude, they have the same module, and they're pointing the same direction. So those vectors are equivalent. So you can just move them over space. They will be equivalent, because we are not distinguishing them in a system of coordinates. So if we, for example, let's say we have minus vector A, that will be pointing from P5, so the 0.5 to 0.6. So they would have the same magnitude, but they would be B would be pointing in the opposite direction of A, right? So that's basically how do you represent vectors. And later on, we will use a system of reference to be able, to represent them in a 2D or 3D space. So with these vectors, what we can do, I mean, we would need to, add things, right? Because you can add forces, we can add displacements, we can basically add a vector. So the way we add this vector is placing the second vector. Let's say we do A plus B, placing the second vector at the end of the arrow of the first one, respecting, of course, the orientation, and then connecting the starting point of the first vector with the ending point of the arrowhead of the second vector. So we have C equal A plus B, right? Just take a look and see that if we do B plus A, we still get C, right? So of course, a vector addition is commutative, and And notice that basically C is the diagonal of the parallelogram that you get of when you get A and B starting from the same point. And we can add two vectors, for example, that are parallel. So you'll get a parallel vector to them, which is just the addition of the two modules. And of course, we can add two vectors that are opposite, right? So we have A plus B, so we can connect the tail of A with the head of B, and we'll get C. If we have these three vectors, this is just another example of how we can commute the vector addition. So we have A plus B, we get D, and then we add C, so we can associate A and B to get another vector, and then add C, so we get R. That would be this example right here. And if we do A, B, C without associating these two, we still get R. And then if we change the order of the sum, so we have B plus A plus C, we still get R. So the same properties that we have with numbers and sum is applying to vectors. Take a look at vector subtraction. So we can, of course, subtract vectors, and subtraction is no more than just, summing the opposites. So that's basically what it is. You just change the direction of the vector that you are that you're subtracting, that you're adding, right? So when you convert it into an addition. Okay, so another property that we can look at is multiplying a number, an actual scalar, with a vector, and that will only change if the scalar is positive, it will only change the module, right? So we will make the vector longer or shorter, right? If it's less than one, that will be divided. But if the scalar is negative, then it will change the direction. It will reverse it. So you have a minus there. So we'll be pointing the other way. Okay, so when we have a vector and we establish a system of reference, then we can calculate the components of that vector. And this is very, very useful and very important in resolving physics problems, because of course, when we have vectors in space, we need to project them into a system of reference. If we don't have a system of reference, we won't be able to calculate anything, and we actually need that. So what we're doing here is just taking the triangle that's formed with the vector and our system of reference, and basically projecting the vector into both axes, x and y. So if we have the angle here, you know that the sine of the angle is the opposite leg of the triangle over the hypotenuse, right? If we have this triangle here, and in order to get the other projection, that will be the x-axis projection, we would use the cosine, because the cosine, of course, is defined by ax. So the adjacent leg divided by the hypotenuse. So remember, the hypotenuse in this case would be the module of the vector. So basically, the projections are the module of the vector multiplied by the sine, if we want to get the y projection, let's say, and the module of the vector multiplied by the cosine of the angle, if we want to get the x projection. look at, I mean, there's two examples. What I'm trying to show here is that if you have the vector pointing, pointing to a different quadrant, which is not the x positive and y positive, it's just the same mechanics, right? Just you gotta keep in mind that the angle is always measured from the x-axis. So you naturally will get the signs of those components. You don't need to add the sign here or add the sign minus here. You just get them from the cosine or the sine when you're calculating the projections. Just keep that in mind, because that's a very common error. You see that this thing is on the negative side of the x and you add a minus, but then you get the minus from the cosine and then the result is wrong. All right, let's move on to, to calculations using the components. So before we define the components, so that will be the easiest way to define a vector, right? Because you can tell someone the magnitude and you can tell the angle, but I mean, it's not that direct or easy to visualize a vector with some specific angle, right? Unless it's 45 or 90 or something like that. But the easiest way to work with vectors would be getting the components. So the components are the projections of the vector into the axis of our coordinate system, as we said before. So in terms of this geometrical layout, we can define the module of the vector as the components, the sum of each component squared, and to that we get the root square of that. So we're basically calculating the hypotenuse of the triangle that the vector defines in this system of reference. So that's how we can calculate the module from the components of the vector. And that would be, the reverse doing from what I showed you in the past slide. And something to bear in mind is how we define the tangent. That would come handy in problems too. The tangent of the angle theta that I showed you before. That's the the opposite leg over the adjacent leg. So that will be the coefficient between the y component and the x component. Then if we want to sum a vector, as we've seen before, graphically it's pretty straightforward, but of course we cannot stick to graphics. We need to have a nice description of the vectors. So what you normally do is sum component by component. So if you look at this, we are summing A and B, so we have A plus B. So we have the components of A and the components of B, right? The smaller vector here, we have Bx, By. So if we take a look at R, the components of R are going to be Ax plus Bx and Ay plus By. So we can get the vector, the sum vector R, by summing the components of each of the vectors. So we have Rx, Ax, Bx, Ry, Ay plus By, and you can totally see it in this graph, and that will apply to any vector, and that will apply to any dimension, because of course we are just talking 2 dimensions here, but you can have vectors of n dimensions. Okay, and then we can look at what happens when you multiply by a scalar, and that will be pretty straightforward too. So if you multiply a scalar if you multiply a vector by a scalar, you can multiply each of the components and you'll get the result vector. All right. Okay. So in order to moving on with our system of reference, it's fundamental to define these unit vectors. So we will express any vector in our system of reference based on this unit vectors, meaning that they are called unit vectors because they have magnitude of 1. So they have no units, they're just a 1. So they are just defining the direction of that component that you are using to describe your vector. So any vector can be expressed or written by the sum of a scalar by multiplied by each of these unit vectors, right? So if we want to express the vector, let's say in this graphic, the vector A would be AX, meaning the component X in the X axis, multiplied by the vector I, which has magnitude 1, meaning that this component would only copy the direction of that vector I, it won't change the magnitude, so AX, plus AI by J. So we have vector J, which is showing the direct, which has direction parallel to the y-axis, and then it will create this component vector AY by J, which has the magnitude AY. So if we sum those two vectors, remember that we have the diagonal of the rectangle in this case, because we are in a system of reference, which is orthogonal, and we get the vector A. Is that clear? That's the way we're gonna represent vectors in a system of reference. We always have the unit vectors that will help us describe the actual vector that we want to use. Okay, and of course, if we want to sum two vectors in this space, we can sum each of the components, and the components are going to be multiplied by the unit vectors. Now let's look at these two characteristics, which are pretty fundamental in physics and are widely used in a lot of descriptions of the physical world, which is the scalar product or a dot product of two vectors. So before we talked about a quantity, a number, just a scalar, which is multiplied by a vector. But now we're multiplying two vectors. So we cannot happily just do something by something and that's it. So the scalar product, as the name is defined, it's calling it, right? It's a scalar number that we get from multiplying two vectors. This is a special product, and it's sometimes you can see it as dot product because you're using the symbol. It's the dot. It's a dot on the, in the middle of the of your writing, basically, not just a dot as a decimal. A dot there, which defines this scalar product, and this is defined as now the multiplication between the modulo of A, the modulo of B, and the cosine of the angle. Whatever, you can call it theta, you can call it phi, you can call it whatever. So that angle would be the angle defined by the two vectors if we arrange them this way. So we have the tail of both vectors together. So the angle is defined by that. And if you take a closer look at this, you'll see that basically is the projection of one of the vectors into the other vector. So let's see here, right? So if we do A times B cosine the angle, we're just getting the projection of B over A. Let's take a look at these other examples. So let's say the angle is bigger than 90. So still we get A the magnitude times b cosine the angle. So we have the projection of b over a, which is here. And if both vectors are, perpendicular to each other, we have the angle at 90 degrees, and we know that the cosine of a 90 is 0. So we have 0 component of b projected to a. Remember, if both things are perpendicular, the projection of each other into each of the directions will be 0, right? So the scalar product of two perpendicular vectors is 0. And down here, we can see that we can actually write the vectors in their, in their components form with the unit vectors. And basically, if you multiply, if you distribute the product, you will arrive to this. Yes. So the scalar product is, you can calculate it multiplying component by component and adding those multiplications. So component x of a, x of b, so you get ax times bx plus ay by plus az bz, etc. So, and so on, depending on the dimension. So the takeaway from this slide is scalar product will always give us a number, which is a scalar. And it's always being done with two vectors. So this is the way to multiply two vectors and to get a number, which is the modulo of one multiplied by the modulo of the other by the cosine of the angle between them. And another way that you can calculate this using the components is basically multiplying component by component and summing. Yes. Okay. Now let's take a look at the other kind of product that we can get with two vectors, which is the vector product. And this will be our last slide for today. So the vector product, or sometimes called cross product, because it's symbolized by a cross here, a tilde cross. It's defined as the modulo of a multiplied by the modulo of b multiplied by the sine of the angle that's between them. But remember, this will be a vector product. So the result is going to be a vector. So this is only the module of the vector that we get from multiplying both a and b. The direction, so of course, remember, we have the module. Now we need the actual direction of the vector that we're getting. So the direction will be defined by the rule of the right hand. The rule of the right hand tells you that if you form a plane with the vector a and the vector b that you are multiplying, and then you place your right hand and go from the first vector to the other, sweeping that angle phi, then the direction of the vector that you're getting is the direction where your thumb is pointing. So if we do a multiplied by v, the vector product between those, we get the module defined by this, and the direction is defined by the rule of the right hand. Of course, if we define a plane in this way, though the vector product between two vectors is gonna always be perpendicular to the plane that those two vectors define. The thing is to know, the direction, the orientation, let's say, that vector will have. And we can take a look and we can see that the product, the vector product, is not commutative. It's anti-commutative, because if we do A multiplied by B, we get a vector pointing up. But if we do a B multiplied by A, now the spanning of our palm, right? It will sweep the angle from B to A. So the thumb will be pointing down. So now the direction of the vector will be pointing down. So it will be the opposite, right? So we can say that this is anti-commutative, because A multiplied by B equals minus B multiplied by A. If we do minus B, of course, we're going to have B pointing that other way, right? And we do minus B times A will span the right way, and it will point up. Yes. So again, this is very, very, very common in physics. This is these two, vector product and scalar product are widely encountered in physics. And of course, we can look at the components of each vector, and we can do the multiplication term by term. So if we write this vector A and B on their components with the unit vectors y, I, j, and k, we can just distribute the product. And of course, remember, that will be a vector product. So you can arrive to this thing down here, where you have the product vector, the vector product described by each of the components multiplied by a unit vector. And of course, we don't need to memorize this thing here. There is a way to calculate which I'm gonna show you right next in this in the last 15 minutes of class. Are we good? Any questions? Any concerns? Anything about, asked today before we get further into the course in terms of the logistic of the course or vectors? Okay. Let me connect with the tablet so I can show you some stuff. In this minutes. Oh, I haven't told you, but the lectures too, I'm gonna upload them in PDF after each class, so you can access that through Brew and Learn.
Recording in progress.
Enable shows. Yes, thanks for letting me know. Now you can hear me. Right. Okay. I was saying that we're gonna go over some of the problems of the sheet of the problem sheet. So if you can download it to have it handy and take a look of what I'm telling you, that will be awesome. The problem sheet I'm gonna upload them to on the Bruin Learn. So I already uploaded the first and second, which is the whole week. So you can start going through those problems. All right, let's see. We can do I mark I think problem 6 that I have. So yeah. Okay, so we can take a look at problem 6. So problem 6 says obtain the value of m such as the vectors a and b are perpendicular, right? So we have vector a, which is -7 I kj minus 11k there. So we have the 3 components, and we have the vector written in terms of the unit vectors, right? So we have vector v. Oh, sorry, I'm copying copying different vector. This is 3i times 9j plus mk, which is what we wanna figure. And then b is -5i. No, this is not homework. The homework will be the multiple choices. This is just some problems that are gonna go over the last part of the class, which is just 10 minutes, the last 10 minutes. Just to, you know, apply something that we've seen in class. Okay. And -8j plus 10k. Okay, so we have those 2 vectors, and the thing is telling us, the problem is telling us that these 2 are perpendicular. So let's obtain the value of m such these 2 are perpendicular. And I have the numbers here, so I'm not calculating anything live, but as we've seen, we have a if we multiply these 2, a and b, and do the scalar product, we have the module of a and b. Let me just do this. So we have so we go faster. We have each one of the modules, and that should be multiplied by the cosine of the angle between those 2. So that is 0 because they are perpendicular, as we've seen in like 3 slides, 3 in the past slides. And so we want a times b, a multiplied by b, as the calculating the scalar product. We want it to be 0. So if we multiply, if we calculate, you know, the scalar product between those 2 vectors a and b, we can do so by multiplying each of the components. So if we do the x component of a times the x component of b, we have this term here. Then we sum the y component of a and y component of b multiplied to each other, and then we have the z component of m and the z component of b, a and b. So we have this term here, and that should be 0. So that's basically what we're doing here. So we are forcing the scalar product to be 0 because we want these vectors to be perpendicular. So from that, we get an equation that we can just clear M out. So if you have any doubt on that, just, sum 15 on the side, subtract 72 on the other side, and then divide by 10. And then you have the value of that. And that's problem 6. Something I haven't told you is that at the end of each of the problem sheets, you're gonna have the solutions of the problems. What's negative? The number 5.7. It's you have. Oh yeah. 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 Awesome. Okay. Let's look at problem 7. And here we can take a look at how do we do product vector, calculate the product of two, the vector product of two vectors. So let's look at 7. 7 says obtain the vector product of A and B. And basically we need to arrive to the component by component representation of that vector product. So we have vector A and vector B, and we have each of the components here. And what's normally then is just this matrix representation is used to calculate those terms of the multiplication to the unit vector. So as I said before, it's not necessary to memorize that expression. So there are different ways to do this, but basically what you do is write the matrix composed by the vector I, J, K, that's here, I, J, K, and then we have each one of the components written here, 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 and here. Right. So then you write again I, J, K, and then the first component of the components of the first vector.
Professor.
Let me do it again here. So we have I, J, K, -2, 11, 5, 10, 3, -9, right? So those are the components of A, the components of B. And then what you can do is, if you want to calculate the first term, you just calculate the first matrix, blocking this two column and row. So you have the matrix. Anyone know the component next to this one? 11. Oh, sorry. You mean the second component of the vector A? Let me open this. Yeah, 11. Yeah, maybe I'm moving too much the tablet and it's not updating. Okay. So I'm gonna go down here. Yeah. Okay, so what I like to do is write again ijk and the first components of the vector that you're multiplying. And then what you do is, calculate the determinant of the matrix. The determinant of the matrix is, let's say we have this matrix 11, 5, 3 minus 9 here. So if we calculate the determinant of that matrix, it will be 11 multiplied by minus 9 minus 3 multiplied by 5. So that's the determinant of that matrix. And that is the first term that we are multiplying by the vector I. So that's the first component of the vector product that we are calculating. Are we clear about that? So in order to calculate the other component, the J component, what you do is get rid of the column and row that's defined with the J component and calculate the determinant of the matrix that you have left. So you have 2, 5, 10, minus 9. Right? So that's minus 2 times minus 9 minus 10 times 5. And that's the other component of that. Yeah. And then if we want to calculate the last component, which is the K, we just block that and we keep this matrix here. So that would be minus 2, 11. Sorry, it's kind of close. 11, 10, 3. That would be 2 times 3, 10, 11. And that's the last component here. So this is I, J, and K. So that's how you calculate the components of those vectors. Another way to look at it is, as I had here, up here before. So you have IJK. Let me get rid of this. IJK, the components of your first vector, the components of your second vector, and then repeat IJK and the components of your first vector. When you have that, if you want to calculate the components of the I vector, I mean the in this case the X component of the product, you're going to do this diagonal. So 11 multiplied by minus 9 minus the other diagonal, which is defined by I. So we have 3 by 5. That's another way to look at it without, I mean, it's the same thing, it's just calculating the determinants, but it's a more compact way of looking at it. So that's for I. If we do, let's say J, if we want to calculate the Y component, then you're going to look at this J down here. So you're going to have this diagonal 10 by 5, and then the other diagonal minus 2 by minus 9. Right? And if you want to calculate the last one, which is K, you're going to take a look at this too. So K, we need this diagonal first, as I'm showing with this arrow. And then you need the other diagonal, which is this one. 10 multiplied by 11, the other one. Always with a minus sign there. So that's the practical way to calculate the vector product between two vectors. And well, I guess we're on time. And do you have any questions about this? It's pretty straightforward. It's just practice, math practice. But on the next class, we're gonna go into actual physics. Of course, you can now get the homework done because it's enabled in the Bruin Learn through the Pearson's website. So just let me know if you have any problem to log in there, and the homework will be due I think yeah, for each incorrect attempts on let me stop this 1 second. Yeah, so for for each one of the questions, I really don't remember exactly because I made them you know, like an integral thing, but exactly I don't know. They have a percentage on each one of the multiple choices. So there, it's not that there's 100 questions and you get, you know, 1 point deducted from each question, but it's weighted in you know, in the average of the whole thing. Exams will be problems just like the problems from the problems sheet. There won't be any big difference. Probably 3 problems or something like that, with maybe some question about, you know, some conceptual question. Yeah, let me just a sec. Sorry, I missed that last one. Oh, will discussions work? Well, I would like Kate to tell you about that, but discussions, so RTA, Kate Holwick, she's gonna propose some problems for that discussions. And basically, you're gonna work on those problems, and then after the discussion, just submit the work you've done. You know, like you can just take a picture, or if you've done it in your tablet, just upload that as a PDF, and that will count as participation in the discussion, and that will give you the credit for the discussion. If you're not able to attend the discussion for any reason, just let Kate know, and you'll be able to submit that the work proposed for that discussion, and you'll get the credit for it. Yeah. Okay. Any other question? If not, I'm gonna see you soon. Discussion in case. Well, I cannot tell you if they're gonna be recorded because Kate would say that, but if not, you can upload the work without, you know, attending that specific one, because she'll let you know the proposed problems for that day or for that week, actually. Yeah. The worksheet, well, you mean the worksheet, like the problems are taken from the problem sheet that it's already posted, and she will tell you which one she's gonna go through. The office hour, my office hour for this week is gonna be tomorrow at 2:30, because that's not gonna be fixed. It might change. I'll let you know as soon as I can. Tomorrow 2:30, and Kate's Fridays at 9 a.m. Any other question? Okay, I'll stop